Let me tell you a story tonight, not of people nor places, but of something far greater. A question as old as thought itself, drifting like stardust through the chambers of every curious mind. How big is the universe really? Before we dive into the unknowable depths, take a moment to like and share this journey, so that others too may pause beneath the stars and wonder. Now close your eyes if you like, or keep them wide open as we begin our voyage through space, time, and the vast silence in between. It begins with darkness, not the kind found beneath closed eyelids or in the absence of light, but a darkness more complete, more ancient, a stillness that predates the stars themselves. Before there were galaxies, before there were atoms, there was a void, expansive and motionless. And then something happened, a sudden shimmer, a whisper of energy swelling in nothingness. The Big Bang. Not an explosion, but an expansion of space itself, of possibility, of everything. From a point of infinite density and unimaginable heat, the universe burst forth, not into empty space, but creating space as it went. In the earliest seconds, it was smaller than a grain of sand, then larger than a galaxy, inflating faster than the speed of light, carrying within it the seeds of time, of gravity, of stars yet to form. The laws that govern reality were forged in those first breaths. The rules of thermodynamics, the parameters of light, the curvature of space. With each flicker of a particle, the universe unfolded. As the cosmos cooled, protons and neutrons found one another, forging the nuclei of simple atoms. In a sea of fire, hydrogen and helium emerged, floating in a furnace still radiant from its birth. But for hundreds of thousands of years, light could not travel freely. The universe was opaque, dense with a fog of charged particles. Then came the moment of recombination. Electrons settled into atomic orbitals. The fog lifted, and light, pure, ancient light, escaped into the widening void. It still travels now, that light, stretched and softened by time, whispering the secrets of creation in microwaves that ripple through the sky. We call it the cosmic microwave background, and in its grainy patterns, cosmologists trace the baby steps of the universe. They measure its age, 13.8 billion years, and its expansion, but those are only numbers. What we seek to grasp is something deeper. Scale. What does it mean to exist in a universe so vast? It takes light, the fastest thing known to physics, billions of years just to cross it. Let us begin small, with Earth. Our blue sphere, cradled in a pocket of space 93 million miles from the sun, spins and orbits in graceful rhythm. The sunlight we feel on our skin each day is 8 minutes old. That same light reflects off our oceans, off moonlit clouds, and then fades into space. Beyond Earth lies the solar system, planets circling a single star, tethered by gravity, bound by invisible lines of force. It is easy to imagine this system as the center of everything, but it is not even close. Beyond Pluto, the heliosphere begins to fade. Interstellar space begins where solar wind no longer holds sway, and yet the stars remain still far away. The nearest one, Proxima Centauri, lies over 4 light-years from us. If the solar system were the size of a coin, the nearest star would be another coin lying several football fields away. We build observatories, both on mountaintops and in orbit, to map the heavens. The Hubble Space Telescope, orbiting above Earth's haze, peers into the past. Each image it sends is a time capsule. The deeper we look, the older the light. Some galaxies appear as they were when dinosaurs roamed Earth. Others, fainter still, hail from a time when no galaxies had yet taken shape, when hydrogen clouds gathered under gravity's gentle pull, preparing to ignite into the first stars. Each galaxy is an island of stars, billions, sometimes trillions, swirling in spirals or stretched in elliptical forms. Our Milky Way alone houses some 100 to 400 billion stars and spans 100,000 light-years across. To cross it at the speed of light would take longer than the entire history of human civilization. And yet, it is but one among hundreds of billions. Between the galaxies lies even more space, vast voids where light seldom travels, and matter is scarce. But even here, the universe is expanding. Galaxies flee from one another, not by motion through space, but because space itself stretches, pushing them apart like dots on a balloon being inflated. The farther a galaxy is, the faster it seems to recede. At extreme distances, the speed of this expansion surpasses even light, not breaking the laws of physics, but bending the fabric of space itself. This discovery of expansion wasn't obvious. For centuries, the night sky seemed fixed and eternal. It was only in the 20th century that Edwin Hubble and others realized that the redshift of light from distant galaxies signaled movement away. The universe wasn't static, it was growing. And here we begin to approach a paradox. If light takes time to travel, and the farthest galaxies we see are 13 billion light-years away, does that mean the universe is only 13 billion light-years wide? Not quite. Due to the expansion of space, those galaxies have moved further away in the time their light reached us. Cosmologists estimate the observable universe, the part we can, in theory, see, to be about 93 billion light-years in diameter. But what lies beyond that? We do not know. Perhaps more galaxies stretching infinitely, or perhaps a boundary, beyond which space curves in upon itself. It's possible, some say, that the universe is infinite. Others suspect it wraps around. Like the surface of a sphere, a three-dimensional shape curved in higher dimensions. If you could travel far enough in one direction, might you return from the opposite side, like an ant walking a globe? Such questions remain open. Yet even within the observable universe, the scale defies comprehension. If every grain of sand on Earth were a star, we would still not match the number of stars in the universe. And each star, perhaps, holds its own planets, worlds unknown, stories untold. Somewhere, light from a distant sun begins its journey, passing through dust clouds bent by gravity, redshifted by expansion. It may never reach us, or it might arrive millions of years from now, finding Earth changed or empty. As we reflect on such distances, we must also remember the time it implies. Looking into space is looking into history. Every photograph of a galaxy is a glimpse into its past. The farther we peer, the younger the cosmos appears. And there lies a boundary we cannot cross, the edge of the observable. Beyond it, space continues, but light has not yet had time to arrive. The universe may be infinite, or it may be bounded by laws we do not yet understand. But the question remains, how big is the universe really? Not just in miles or light years, but in meaning. What does it mean to live in a cosmos so vast that even light becomes a thread of history? What does it mean for consciousness to arise, fleeting, fragile within such immensity? The journey has only begun. The deeper we go, the more the question unfolds. Let us keep traveling, beyond the stars, beyond the galaxies, into the fabric of reality itself. We now leave behind the comforting scales of solar systems and galaxies, and step into something even more elusive, structure beyond form, patterns stitched across the cosmos with invisible threads. It is not merely a universe of stars and light, but of architecture, grander and more abstract than we can touch with our hands. Galaxies, those immense cities of stars, do not float in isolation. They form clusters, congregations bound by gravity, dozens, sometimes thousands, orbiting mutual centers like spiraling bees to a distant, invisible queen. And these clusters themselves are bound into even larger structures, superclusters, stretching across hundreds of millions of light years, forming a web, a cosmic web. This web is not woven with silk, but with gravity, dark matter, and time. Its filaments, thread-like chains of galaxies, arc across the blackness, linking luminous nodes like beads suspended in space. Between them lie voids, great yawning spaces, nearly empty of galaxies, each hundreds of millions of light-years across. This contrast, this structure, this lattice of matter is not visible to the naked eye. But through gravitational lensing and redshift surveys, we have traced its contours, revealing a pattern that speaks of an origin both chaotic and ordered. The cosmic web is perhaps the greatest fingerprint of the early universe, a relic of quantum fluctuations, amplified by gravity and the relentless expansion of space. Within it we find meaning, but we also find mystery. For this grand arrangement, for all its elegance and scope, is shaped by a force we do not see: dark matter. It outweighs all the visible stars, all the glowing gas, all the atoms we've ever catalogued. By a factor of 5 to 1, dark matter dominates the mass of the universe. Yet it emits no light, reflects none. It passes through us, through planets and stars like a ghost in the machinery of reality. We infer its presence only through its pull, its silent orchestration of galactic dance. Dark matter sculpts galaxies, preventing them from unraveling as they spin. It glues clusters together. Without it, the universe would look different, emptier, quieter, scattered. And yet, for all our instruments and insight, we do not know what it is. WIMPs, axions, sterile neutrinos, our theories multiply, but confirmation remains elusive. The darkness in the sky is not mere absence. It is presence, abundant and fundamental. And beyond even dark matter, there is a greater mystery still: dark energy. When astronomers measured the expansion of the universe with ever more distant supernovae, they expected to find it slowing, dragged by gravity's long arm. Instead, they discovered acceleration. Space was not merely stretching, it was speeding up. Galaxies were not just moving away, they were being flung faster and faster into deeper separation. The cause? An unknown energy permeating space itself. Dark energy is not just somewhere, it is everywhere, embedded in the vacuum, tugging outward, against gravity. It accounts for nearly 70% of the total energy of the universe, yet we do not know its nature. Is it a property of space, a quantum field, a cosmological constant? Einstein once proposed such a constant, then abandoned it, thinking it a mistake. Now it returns, not as a patch, but as a profound truth. The universe, it seems, has a destiny, endless expansion, driven by dark energy. The galaxies we see today will drift beyond reach. Light from them will never arrive. One day the sky will darken, not because stars have died, but because space has expanded so far that their light no longer finds us. This fate, cosmic isolation, is not immediate. It is written in the script of eons yet to unfold. But even now, it reshapes our understanding of size. The universe we can see, the observable sphere with a radius of about 46.5 billion light-years, is not all there is. It is merely the part that light has had time to reach. But beyond that shell, space continues, expanded, unreachable perhaps, infinite. And in that word, infinite, we find the edge of language. What does it mean for something to have no end, to expand without limit? Our minds are built from finite things, seeds and stars and cities, and the infinite slips from our grasp. But cosmology insists the universe might be infinite in extent. That is not to say everything exists, only that no boundary has yet been found, and none may exist. Some theories suggest a multiverse, a collection of universes, each with its own laws, its own constants, perhaps even dimensions beyond our own. In some models, inflation, the rapid expansion following the Big Bang, did not end everywhere. Pockets of space kept inflating, spawning other universes like bubbles in an endless foam. Our universe would be one bubble among countless others, each floating in a higher dimensional space. But we cannot see these other universes. Not now, perhaps not ever. They lie beyond our light horizon, beyond the reach of any signal. Yet the mathematics that describe them are not fantasy. They emerge from attempts to explain what we do see. And so, the boundary between science and imagination becomes blurred. Still, even within our own cosmic bubble, the scale is breathtaking. Imagine shrinking Earth to a marble. The solar system becomes a room. The Milky Way, a continent. The observable universe, a globe larger than Earth's orbit. Each step in scale dwarfs the last. We live on one world, orbiting one star, in one galaxy. Yet there are more galaxies than we can count. Hubble's Deep Field, a photograph taken by pointing a telescope at a dark patch of sky, revealed thousands of galaxies in an area no larger than a grain of sand held at arm's length. Every patch of sky, no matter how empty it seems, contains such depth. It is not the stars that are rare, it is the silence of seeing. And in this silence, the question continues to echo. How big is the universe really? It is as big as the speed of light allows us to see, as big as space can stretch, as big as our questions can reach. Yet perhaps its true scale is not measured in distance, but in wonder. For we stand on a pale blue dot, as Carl Sagan once said, suspended in a sunbeam, and we dare to ask what lies beyond the dark. We launch probes, build telescopes, write equations. We trace starlight, measure shadows, test gravity's grip. And with each answer, more questions rise. Each discovery expands not just our knowledge, but our ignorance. For the universe is not a problem to be solved, but a reality to be encountered, endlessly, humbly, and with awe. Let us journey further, into time itself, and ask how the universe grew, not just in space, but in complexity. The question of size is inseparable from time. To ask how big the universe is today is also to ask how it became so, and what happened in the unimaginable span between the very beginning and this moment. Now as you sit listening, thinking, breathing, on a small planet tucked into the corner of a spiral galaxy, to understand the scale of the universe, we must trace its expansion through epochs. We must witness time not as a line, but as a blossoming, a rhythm, a breath held and then released. We must look back not just through space, but through history itself, back to the first instant when there was no space, no time, no matter, no energy, only potential. The universe began not with an explosion, but with expansion. This distinction matters. Explosions burst into space. The Big Bang created space. It was not a fireball in the void. It was the void becoming form, silence giving way to vibration. In the first trillionth of a second, the universe underwent a phase called cosmic inflation, expanding faster than the speed of light, stretching quantum fluctuations into the seeds of galaxies. This inflation set the stage, like a drum skin stretched tight before the first strike. Then inflation ended. The universe reheated. Particles emerged. The fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, broke from their original unity. The cosmos was a seething plasma, too hot for atoms, too dense for light to travel freely. Time passed. Minutes after the beginning, protons and neutrons fused into the first nuclei, hydrogen, helium, traces of lithium. Still, no atoms. The universe was opaque. For nearly 380,000 years it remained so. Then, as it expanded and cooled, electrons finally settled into orbit around nuclei. Atoms formed. The fog lifted. Light decoupled from matter. This is the cosmic microwave background, a faint afterglow still detectable today, whispering of a time before stars, before galaxies, before darkness had faces. It is a message not from beyond the universe, but from its infancy. From that moment, gravity began its slow, relentless work. Slight variations in density pulled matter toward itself. Over hundreds of millions of years, gas gathered, collapsed, ignited. The first stars were born, huge, luminous, short-lived. They forged heavier elements in their cores, carbon, oxygen, iron, and died in brilliant supernovae, scattering their enriched ashes into space. Galaxies coalesced, clusters formed. Light blossomed across the universe. Billions of years passed. More stars were born. Planets formed around them. Some of these planets were rocky. Some held water. On one such world, around an unremarkable star, life began. It took time, more than 4 billion years, for that life to open eyes and ask where it was, and what it meant. To point telescopes at the sky and seek answers not in myth alone, but in evidence. From the moment of that first sight to now, humanity has reached outward with curiosity and inward with reflection. Our understanding of the universe is a mirror. We see its scale, and in it, we see the smallness and grandeur of our own condition. Now let us pause to measure time itself, not in minutes or hours, but in cosmic epochs. The universe is roughly 13.8 billion years old, but because it has expanded over that time, the observable universe stretches 93 billion light-years across. How can this be? Because space itself stretches. A galaxy whose light took 13 billion years to reach us has continued to recede in that time, so its current distance may be over 30 billion light-years away. This expansion is not into space, it is space itself unfurling. There is no edge, no center. Every point recedes from every other, and so the observable universe is not a complete picture. It is a horizon beyond which lie galaxies whose light will never reach us, no matter how long we wait. It is like standing on a vast plain at night, watching distant lanterns drift away, until their glow fades forever. The darkness between them grows. This is not just poetry, it is physics. Dark energy is accelerating this drift, pulling the very fabric of the universe apart. Eventually, even nearby galaxies will vanish from view. But this is the future. What of now? Within the observable universe, astronomers estimate there are roughly 2 trillion galaxies. Each galaxy holds billions or trillions of stars. Multiply that by the number of likely planets around those stars, and the scale becomes almost meaningless. More than all the grains of sand on Earth, more than our imagination can stretch. Yet each one of these stars, these galaxies, these particles, obeys the same laws, the same constants, the same physics that we test in labs and accelerators. This uniformity is one of the great mysteries. Why should distant corners of the universe, too far apart to have communicated, appear so similar? Why is the cosmic microwave background nearly the same temperature in all directions? Inflation theory helps answer this. If the universe expanded rapidly from a small, causally connected region, it could imprint that uniformity across vast scales. And yet we know the universe is not entirely smooth. The fluctuations in temperature, in the cosmic microwave background, the tiny bumps and ripples, are the fingerprints of those early quantum fluctuations frozen into the sky. They are the seeds from which all structure grew. Without them, there would be no galaxies, no stars, no us. So the scale of the universe is not merely spatial, it is ancestral. We are descendants of fluctuations, children of imperfection, born from unevenness, from imbalance, from the way energy pooled in one spot and not another. In this sense, the scale of the universe is also the scale of chance, and within it, something else stirs. Intelligence, awareness, the ability to reflect, to imagine, to calculate. We build machines to detect distant exoplanets, to measure gravitational waves, to map the distribution of matter billions of light years away. Our minds, fragile as they are, reach across scales that once seemed reserved for gods. This reaching is not just scientific, it is emotional, spiritual. To grasp the scale of the universe is to feel small, yes, but also connected. For every particle in your body was forged in stars. Every atom of iron in your blood was born in a supernova. You are not merely in the universe, you are of it. So when we ask how big the universe is, we are asking something more. We are asking, what is our place in all this? What does it mean to be alive, aware, in a reality so vast and so ancient? And we are not done asking. The next frontier lies not just in space, but in understanding the fundamental nature of space and time. Are there dimensions beyond the familiar? 3. Is the fabric of space-time smooth or granular like pixels on a screen? Is the universe deterministic or probabilistic? Is it finite or infinite? And if infinite, does it repeat? Are there copies of us, distant and unreachable, living parallel lives? These are not idle speculations. They arise from serious physics, from string theory, loop quantum gravity, and other attempts to reconcile general relativity with quantum mechanics. They suggest a universe more strange than anything we've imagined, perhaps one where space itself emerges from information, from entanglement, from patterns beyond geometry. We stand at the edge of knowing, and yet the edge recedes as we approach. The more we learn, the more we see how much lies beyond. Let us continue. In the next part, we will explore the strange nature of time itself, and how the passage of time shapes what we mean by size. To understand the size of the universe, one must also understand time, not merely as it passes on a ticking clock, but as a dimension that stretches, bends, and warps alongside space. In Einstein's universe, space and time are not separate. Arenas in which matter dances, they are part of the same fabric, the same woven geometry that responds to the presence of mass and energy. Space tells matter how to move, matter tells space how to curve, and time, our ever-present companion, is embedded within that curvature, not constant but elastic. Imagine standing near a massive object like a black hole. Time for you slows relative to someone far away in space. This is not science fiction, it is measurable. Astronauts aboard satellites age just a tiny bit slower than people on Earth. GPS satellites must correct for this effect constantly, or they would steer us off course. These relativistic principles reveal something extraordinary. Time is not universal. It does not tick uniformly everywhere. It stretches and compresses depending on gravity and motion. So when we ask how old the universe is, 13.8 billion years, we are referring to a kind of average cosmic time. But from the perspective of light traveling through the expanding universe, time behaves differently. Light emitted from a galaxy 13 billion years ago has been stretched, its wavelength elongated by the expansion of space. What began as visible light may arrive as microwaves. This redshifting is not due to the galaxy moving through space, but space itself stretching as the light traverses it. This brings us to one of the most beautiful aspects of cosmology. The light we see is ancient. When you look at the night sky, you're looking into the past. The moon is 1.3 light seconds away. The sun, 8 minutes. The nearest star, 4.3 years. The Andromeda Galaxy, 2.5 million years. When you gaze at it, you see it not as it is, but as it was when early humans first began shaping stone tools. The further we look, the deeper into time we peer. Our most powerful telescopes are time machines, revealing epochs when the first stars were born, when galaxies first spun, when the universe was young and wild. And yet, paradoxically, the universe today is older and larger than we ever imagined. Its expansion does not slow. It accelerates, pushed apart by dark energy, a mysterious force that seems to pervade empty space itself. The discovery of this acceleration in the late 1990s shocked the scientific world. It meant that the ultimate fate of the cosmos would not be a gradual slowing and collapse, but a lonely drifting, an eternal stretching of space that would one day isolate galaxies from each other. Let us visualize this in human terms. Imagine you're standing in a vast hall filled with glowing lanterns, each one a galaxy. At first, the lanterns are clustered close, casting overlapping shadows. Then, slowly the hall expands, the lanterns drift apart. Their light still reaches you, but over time fewer and fewer remain visible. Eventually, only the closest remain. The distant ones, though still burning, are too far for their light to reach you anymore. The universe becomes a lonely place. This cosmic loneliness awaits us in the far future. 1 trillion years from now, distant galaxies will fade from view. The sky will go dark. Future civilizations may grow up in isolated islands of stars, unaware that the universe was once filled with countless galaxies. They may believe theirs is all that exists, and unless they recover the ancient records, our maps, our data, they may never know the truth. But we know it now. We live in a unique moment, a narrow window in cosmic time when the light from distant galaxies still reaches us, when the sky still speaks of the universe's vastness. We are cosmic witnesses, custodians of perspective. And that makes this moment precious beyond measure. The universe, then, is not just vast in space, It is vast in history, vast in futures yet unborn. But it is also vast in another, subtler dimension, the dimension of possibility. Consider the multiverse, a speculative but mathematically plausible concept arising from inflation theory and quantum mechanics. The idea is this: our universe may not be all that exists. It may be one bubble in a frothing sea of other universes, each with its own physical laws, constants, and outcomes. Some may be barren, others may teem with life. In some, gravity might be stronger. In others, atoms may never form. If this multiverse exists, then the size of our universe is no longer the final word. It is but one thread in an infinite tapestry, a single verse in a cosmic poem without end. And we, who live within this verse, are just beginning to hear the rhythm. Even within our own universe, there are mysteries hidden from view. Dark matter, for instance, outweighs visible matter 5 to 1. We know it exists because we see its gravitational effects, galaxies spinning faster than their visible mass would allow, light bending around clusters in ways that suggest more mass than we can see. But what is dark matter? We do not know. It does not emit light. It does not interact with ordinary matter in familiar ways. Yet it is everywhere, forming halos around galaxies, shaping the structure of the cosmos. And then there is dark energy, utterly mysterious, yet dominating the universe's behavior on the largest scales. It is not simply energy in the vacuum. It is a force driving galaxies apart, overcoming the pull of gravity. It shapes the geometry of space itself, flattening it, influencing its destiny. So we live in a universe where most of what exists is invisible, unknowable, at least for now. We are surrounded by the unseen. And yet, from this small corner of the cosmos, we map the heavens, measure the relic radiation of the Big Bang, trace the filaments of galaxies across billions of light years. This is the paradox of our condition. We are infinitesimal, yet capable of grasping the infinite. We are momentary, yet aware of eternity. Our lives are brief flickers, yet we use them to illuminate the darkness. And in doing so, we become part of the universe's story, not as passive observers, but as conscious participants. Every equation we write, every telescope we launch, every question we ask is a gesture of defiance against ignorance. It is a spark in the void. So how big is the universe? It is larger than light can travel in its entire lifetime. Larger than time allows us to see. Larger than the sum of all visible galaxies. It is the size of our wonder, the size of our yearning, the size of a question that may never be fully answered, yet must always be asked. In the next part, we will dive deeper into the structure of the cosmos, examining galaxy clusters, filaments, voids, and the great web that binds it all together, revealing the universe's grand architecture. To measure the true immensity of the universe, we must now peer beyond individual stars and galaxies, and instead consider the grand architecture of matter on the largest scales. What we discover is not chaos, but an intricate structure woven like a cosmic web, a vast network of galaxies strung together across billions of light years, forming nodes, filaments, and voids in a pattern both majestic and mysterious. At the eye's heart of this structure are galaxy clusters, enormous congregations of hundreds or even thousands of galaxies bound together by gravity. These clusters are not evenly scattered. Instead, they gather along elongated threads known as filaments. These filaments, in turn, thread their way around immense regions of emptiness known as cosmic voids. When observed on scales of hundreds of millions of light years, this distribution of matter resembles a sponge, or more profoundly, the interconnected synapses of a brain. We call this arrangement the cosmic web, and it is among the most awe-inspiring features of the known universe. Simulations based on dark matter, gas dynamics, and gravity show that this web-like structure emerged from the primordial fluctuations of the early universe, tiny ripples in the density of matter that grew, through the force of gravity, into the vast filamentary networks we observe today. To put this scale into perspective, Consider the Laniakea supercluster, our home supercluster. It spans over 500 million light-years and contains over 100,000 galaxies, including the Milky Way. And Laniakea is not unique. It is part of an even larger network, connected to other superclusters by intergalactic highways of galaxies and dark matter, flowing in a gravitational ballet through the cosmos. The name Laniakea itself means immense heaven in Hawaiian, a fitting title for the realm we call home. Yet even these superclusters are just features on the cosmic map. Surrounding them are voids, staggeringly vast regions where few or no galaxies exist. Some of these voids are over 100 million light-years across. They are not completely empty, but they are eerily underpopulated, like deserts in a universe of cities. Their presence only enhances the significance of the web, outlining the contrasting geometry of fullness and emptiness, light and dark. Our ability to chart this cosmic architecture stems from light, specifically, red-shifted light from distant galaxies. As the universe expands, the wavelength of light stretches, shifting toward the red end of the spectrum. By measuring this redshift, we can estimate a galaxy's distance from us, and using that, we build three-dimensional maps of the universe. These maps show the clustering of galaxies, the walls and filaments, and the great voids, offering us a blueprint of cosmic history. One of the most iconic visualizations of this is the Sloan Digital Sky Survey, which plotted the positions of hundreds of thousands of galaxies. When viewed from above, the pattern resembles a web or lace, delicate and incomprehensibly large. It is in these maps that we find the most distant galaxies, their faint light, arriving from the earliest epochs of time. They show us how matter has organized itself, drawn together by dark matter scaffolding and sculpted by gravity. Indeed, dark matter is crucial in this cosmic arrangement. Although it does not emit or absorb light, its gravitational influence is immense. In the early universe, dark matter clumped together first, creating gravitational wells into which ordinary matter fell, leading to the birth of stars and galaxies. Without dark matter, the cosmic web would not exist. It is the invisible architect of the universe, shaping its skeleton over billions of years. Another layer of structure emerges when we examine galaxy clusters more closely. Many of them contain a hot, X-ray emitting gas that can reach temperatures of tens of millions of degrees. This intergalactic medium contributes significantly to the mass of the clusters and acts as a reservoir of matter that fuels future star formation. In addition, the motion of galaxies within clusters, often moving at thousands of kilometers per second, gives clues to the total mass held together by gravity, including the otherwise invisible dark matter. Gravitational lensing offers further insight. When light from a distant galaxy passes through a massive cluster, the gravity of the cluster bends the light, distorting and magnifying the background image. These cosmic lenses not only confirm Einstein's general relativity, but also allow us to detect and map the dark matter within clusters. What we find reinforces our understanding. The visible galaxies are merely the tips of icebergs, floating atop massive halos of dark matter that bind them together. From these threads and nodes, the universe reveals itself not as a random scattering of stars, but as a vast, organized structure, interconnected, dynamic, and evolving. It pulses with the memory of its own birth and the whisper of its future. Every filament, every void, every shimmering galaxy contributes to this cosmic tapestry, and through the lens of science, we begin to read its patterns. Yet beyond the maps and models, the universe continues to defy comprehension. For every cluster we chart, there are billions more beyond the reach of our instruments. For every light year we measure, space expands further, faster, beyond even the speed of light itself, not in violation of physics, but as a consequence of space itself stretching. This is the strange truth. Galaxies are not moving through space like ships on an ocean. Rather, the ocean itself is expanding, carrying them away from us. The implications are profound. It means that some regions of the universe are receding so rapidly that their light will never reach us. These parts of the cosmos are effectively beyond our observable horizon, not because they don't exist, but because we can never see them. They are outside our cosmic light cone, forever hidden. The universe we can see is not the universe in total. It is merely a sphere of visibility, a bubble of knowability, suspended in a boundless unknown. Current estimates suggest that while the universe is 13.8 billion years old, the observable universe has a radius of about 46.5 billion light-years. This discrepancy arises from the expansion of space. Light from a galaxy emitted 13 billion years ago was emitted when that galaxy was far closer, but as the light traveled toward us, the space between us and it stretched, increasing the distance. By the time the light reaches us, that galaxy is now tens of billions of light-years away. And so, paradoxically, the observable universe is larger than its age multiplied by the speed of light. This is not a mistake. It is the inevitable consequence of a dynamic, expanding cosmos. It means that the true size of the universe might be vastly larger than what we can observe, possibly infinite, or at least so vast that its curvature is imperceptible. In the next part, we will journey deeper into the early universe, through the cosmic microwave background, the relic radiation of the Big Bang, to glimpse the seeds of galaxies and the first hints of the universe's vast design. Long before galaxies coalesced and stars began to shine, the universe existed in a radically different state, a dense, hot, and uniform plasma teeming with particles and energy, all suspended in a moment just after the Big Bang. To understand how this seething cauldron gave birth to the structured universe we see today, we must turn to the faintest and most ancient light in existence, the cosmic microwave background, or CMB. The CMB is not merely a glow in the sky, it is a time capsule from when the universe was just 380,000 years old, a baby in cosmic terms. At that time, the universe had expanded and cooled just enough for protons and electrons to combine into neutral hydrogen atoms, a process called recombination. With the birth of these atoms, the universe became transparent to light for the first time. Photons, which had been constantly scattered by charged particles in the plasma, were now free to travel through space. And travel they did, uninterrupted for billions of years, until they were finally intercepted by our radio telescopes. What we see today as the CMB is this relic radiation, stretched and cooled by the expansion of the universe. Originally blistering, hot, it has since cooled to just 2.725 Kelvin, a whisper above absolute zero, becoming microwave radiation. And yet, despite its faintness, it contains clues as to how everything came to be. The CMB is remarkably uniform in all directions, but it is not perfectly smooth. Embedded within its glow are tiny fluctuations, minute differences in temperature, on the order of 1 part in 100,000. These fluctuations represent the seeds of all current structure, the places where gravity began to pull more matter together, leading eventually to the formation of galaxies, stars, planets, and life. These tiny differences are mapped with exquisite precision by instruments like COBE, WMAP, and most recently, the Planck satellite. The temperature fluctuations correspond to regions of slightly higher or lower density in the early universe. In the denser regions, gravity had a slight advantage and pulled more matter in, starting a long cascade of cosmic architecture that unfolded over billions of years. But even more remarkable than the data itself is what it implies about the shape and fate of the universe. The CMB acts as a screen against which we can project the geometry of space. If space were curved positively like a sphere, distant objects would appear larger than expected. If negatively like a saddle, they'd appear smaller. But what we find, again and again, is that the universe is astonishingly flat, meaning that, on large scales, space itself does not curve noticeably in any direction. This suggests that the universe may be infinite, or at least so vast that any curvature is beyond our observational reach. And here enters the most profound idea: cosmic inflation, to explain the incredible smoothness and flatness of the universe, as well as the origin of the tiny fluctuations in the CMB. Scientists propose that in the first trillionth of a second after the Big Bang, the universe underwent a period of exponential expansion. During this infinitesimal moment, space expanded faster than the speed of light, not violating physics, because it was space itself stretching. Inflation would have stretched out any irregularities, making the universe appear smooth and flat, just as we observe. It also seeded those tiny quantum fluctuations that would grow into galaxies, giving rise to the large-scale structure we see today. This is no longer just a hypothesis. It is supported by multiple lines of evidence, and it has become the foundation of our modern cosmological model. And so the CMB is not only a photograph of the infant universe, it is a bridge between the quantum and the cosmic, connecting subatomic ripples with the galaxies that populate the sky. From these nearly imperceptible variations in temperature and density, the entire observable universe took shape. The delicate balance of matter and energy, of expansion and gravity, of radiation and mass, all encoded in this ancient light. But as we study the CMB more deeply, more mysteries emerge. One such enigma is the axis of evil, a term coined by cosmologists to describe an unexpected alignment in the large-scale fluctuations of the CMB. While it may be a statistical fluke, or perhaps a signal of new physics, its existence reminds us how much we still do not understand about the early universe. Another mystery arises from the fact that some parts of the universe seem to have been in causal contact, meaning they were once close enough to exchange information, despite being too far apart for light to have traveled between them under standard models. Inflation solves this problem by positing that these regions were once close together, before being rapidly stretched apart. We are left then with a cosmic puzzle. The universe appears both infinite, and yet has a knowable edge, the boundary of the observable universe. Beyond this edge, space may continue indefinitely, or it may be part of a more complex, multiversal structure. There might be regions where physics operates differently, where constants vary, or even where entire other universes exist, each born from its own inflationary burst. While the multiverse remains a speculative idea, it is a natural consequence of many inflationary models. If inflation happens once, it might happen endlessly, spawning universe after universe in a grand cosmic foam, with each bubble representing a different reality. Ours would be just one among countless others, each with its own stars, laws, and perhaps even sentient life pondering the same questions. But even without invoking a multiverse, the sheer scale of our own observable cosmos is staggering. The number of galaxies in the observable universe is estimated to be over 2 trillion. Each of these galaxies contains hundreds of billions of stars, and each of those stars may host planetary systems, many with Earth-like worlds. The numbers defy comprehension. There are more stars in the observable universe than grains of sand on all the beaches of Earth, a comparison that, while poetic, still falls short of the reality. And this immense structure, the stars, galaxies, superclusters, and voids, is still expanding. The farther away a galaxy is, the faster it recedes from us, not because of its own motion through space, but because space itself is stretching. This expansion is not slowing down. On the contrary, it is accelerating, driven by a mysterious force we call dark energy. Dark energy makes up about 68% of the total energy content of the universe, yet we know almost nothing about it. It acts like a repulsive gravity pushing space apart. Unlike matter or radiation, its density does not dilute as the universe expands. Instead, it remains constant or even increases. This causes the expansion to speed up, sending galaxies hurtling away from one another with ever-growing velocity. The consequence of this acceleration is profound. In the distant future, galaxies will slip beyond our horizon. The universe will become darker, colder, and more isolated. Civilizations in the far future may see only their local galaxies, unaware of the vast cosmic web that once stretched across the sky. We live in a privileged moment, in a universe old enough to have formed stars and galaxies, but not so old that it has become empty and dark. We stand at a cosmic dawn, able to measure its past and predict its future, using light that has traveled for billions of years to reach our eyes. In the next part, we will explore the mysterious nature of dark energy and dark matter in greater depth, the unseen forces shaping the cosmos and the clues they offer about the ultimate fate of the universe. To speak of the universe's structure without mentioning dark matter and dark energy would be to describe a symphony by its silences. They are the unseen scaffolding and subtle currents shaping the grand architecture of everything we know. While they remain elusive and invisible, their presence is undeniable, their influence written into the movements of galaxies, the growth of cosmic filaments, and the silent acceleration of space itself. Let us begin with dark matter, the invisible hand that holds galaxies together. When astronomers first measured the rotation curves of spiral galaxies, those vast, elegant disks of stars, they expected the stars at the edges to orbit more slowly than those near the center, as predicted by Newtonian dynamics. But instead they found something astonishing. The stars far from the galactic core were moving just as fast, sometimes faster, than those close to the center. This defied all understanding. According to the visible matter in these galaxies, stars, gas, dust, there simply wasn't enough gravity to hold them together at such speeds. They should fly apart like sparks from a spinning wheel, but they didn't. Something unseen was exerting gravitational force, something massive, yet undetectable by light. This unseen mass was named dark matter. Dark matter does not emit, absorb, or reflect light. It cannot be touched, tasted, or seen. Yet it outweighs normal baryonic matter by more than 5-to-1. It lurks in vast halos around galaxies and clusters, shaping the evolution of structure on every scale. Without it, galaxies would never have formed. The universe would be a scattered mist of particles, not the intricate web of stars and galaxies we observe. We detect dark matter through its gravitational effects. It bends light from distant sources, a phenomenon called gravitational lensing, creating arcs and distortions in the images of background galaxies. It alters the motion of galaxies and clusters and changes the pattern of cosmic background radiation. Its fingerprints are everywhere, and yet we do not know what it is. It might be made of exotic particles, WIMPs, weakly interacting massive particles, axions, or sterile neutrinos. It might hint at a deeper layer of physical law we have yet to discover. Experiments deep underground and in space continue to search for it, hoping to catch even the faintest whisper of a dark particle colliding with ordinary matter. But so far, the dark remains silent. Even more puzzling than dark matter is dark energy, which is not simply an invisible mass but a force, an energy intrinsic to space itself. Its discovery came at the turn of the 21st century when two independent teams of astronomers measured the light from distant Type I supernovae, brilliant explosions that serve as standard candles for cosmic distances. These supernovae revealed a shocking truth. The expansion of the universe was not slowing down, as once thought, but accelerating. Something unseen, unknown, was pushing galaxies apart faster and faster. This repulsive force was given the name dark energy. Dark energy now dominates the energy budget of the universe, comprising nearly 70% of its total content. Unlike matter, which clumps and clusters, dark energy is smooth and uniform. It does not dilute as space expands. In fact, it causes the expansion to accelerate, leading to ever-increasing isolation among cosmic structures. What is dark energy? It might be a cosmological constant, an inherent energy of the vacuum, first proposed by Einstein and later abandoned, only to be resurrected by modern cosmology. Or it could be a dynamic field, something akin to the inflationary field that drove the early universe's rapid expansion. It could signal a new kind of force, or even flaws in our understanding of gravity itself. Its effects are subtle yet profound. As space accelerates outward, galaxies drift apart faster than light, not because they are moving through space, but because space between them is expanding. In time, more and more galaxies will pass beyond the cosmic event horizon, disappearing forever from our view. This has dramatic implications for the fate of the universe. If dark energy remains constant, the universe will continue expanding forever, growing colder and darker in a slow, lonely death known as the Big Freeze. Stars will burn out, galaxies will fade, and even black holes will evaporate, leaving behind a void of infinite silence. If dark energy strengthens over time, a scenario called phantom energy, the expansion could accelerate to the point of tearing galaxies, stars, planets, and even atoms apart in a cataclysm known as the Big Rip. Or perhaps dark energy will reverse. Maybe it is a temporary phenomenon, and gravity will one day regain dominance, halting expansion and pulling everything back into a final contraction, the Big Crunch, followed perhaps by a rebirth. We do not yet know which path the universe will follow. What we do know is that dark matter and dark energy shape everything. They are the unseen weavers of the cosmic tapestry, the silent agents guiding the universe from birth toward its end. But in the face of such vast and unknowable forces, what does it mean for us humans, clinging to a pale blue dot, staring into the void? It means that we are part of something unimaginably large, and yet deeply connected. We are born of stars, whose formation was governed by dark matter, living in a universe whose shape is dictated by dark energy. Our atoms, our thoughts, our hopes, they are products of a cosmos both mysterious and majestic. And we are learning. With each passing year, we reach deeper into the darkness, tracing the patterns of invisible forces, mapping the hidden terrain of space and time. We are explorers of the unseen, guided by light from the ancient past, searching for answers written in the silence between stars. In the next part, we will journey into the largest structures the universe has to offer, the colossal cosmic web, superclusters, and the great voids that span hundreds of millions of light years. Here, in the vast geography of everything, we will see how galaxies arrange themselves in patterns that echo the earliest moments of creation. If the galaxies are the cities of the universe, then their distribution paints the map of a vast, unknowable continent, a sprawling terrain where clusters form mountain ranges, voids stretch like deserts, and filaments run like the ancient roads connecting one mystery to another. To glimpse this structure is to witness the grandest architecture ever known, a pattern woven into space itself by gravity and time. This structure is often referred to as the cosmic web. It is the large-scale scaffolding of the universe, a filamentous network composed of galaxies, dark matter, and gas, stretching across billions of light years. And it is not uniform. It is a frothy mosaic of dense knots, where clusters of galaxies gather, and immense voids, regions with scarcely a single galaxy, extending for tens or even hundreds of millions of light years. When astronomers look deep into the universe, using massive sky surveys like the Sloan Digital Sky Survey or the Dark Energy Survey, they find that galaxies do not scatter randomly. Instead, they follow a structure reminiscent of veins or threads, strung along invisible lines of gravitational attraction. These threads are the cosmic filaments, and they connect at nodes, superclusters, gigantic conglomerates of galaxies gravitationally bound into regions that can span 100 million light-years or more. One of the most well-known of these vast formations is the Laniakea supercluster, our home in the cosmic web. It contains our own Milky Way galaxy, along with the Virgo cluster and over 100,000 other galaxies. The name Laniakea means immense heaven in Hawaiian, a fitting title for a region so vast it challenges comprehension. But even Laniakea is just one thread in the larger fabric. Beyond it lie structures of even more extraordinary scale. The Sloan Great Wall, the Hercules Corona Borealis Great Wall, and the Boots Void. These are titanic formations, walls and gaps in the universe that extend for over 1 billion light-years in some cases. How such structures formed in a universe that is just 13.8 billion years old remains one of the most profound questions in cosmology. The idea that the universe is homogeneous and isotropic, that it looks the same in all directions and from every point, was once a pillar of cosmological thinking. But the discovery of such immense formations has pushed the boundaries of that assumption. Are we just beginning to see the larger patterns? Or are these anomalies, rare fluctuations in an otherwise smooth cosmos? The answer remains unclear. The formation of the cosmic web traces back to the earliest moments after the Big Bang. Tiny fluctuations in the cosmic microwave background, ripples of slightly denser regions, grew under the influence of gravity. Over billions of years, they became the seeds of structure, as matter fell into the potential wells formed by dark matter. Where dark matter clumped, normal matter followed, eventually igniting into stars and galaxies. Thus, the filaments and walls we see today are fossil records of quantum fluctuations from a time when the universe was less than a second old. To map this vast web, scientists rely on a combination of redshift surveys, computer simulations, and gravitational lensing. Redshift tells us how fast a galaxy is moving away, which in turn tells us how far away it is. By measuring the positions of millions of galaxies, we can build a three-dimensional map of the cosmos. Simulations like the Illustris Project or Millennium simulation use the laws of physics, initial conditions from the early universe, and billions of digital particles to recreate the evolution of cosmic structure. These simulations confirm what observations suggest. The universe's large-scale structure resembles a sponge or honeycomb, where the luminous matter is concentrated along thin filaments, surrounding vast empty bubbles. Within these structures, galaxies are not static. They dance, fall, merge, and collide. They drift along filaments like leaves on a current, pulled by the gravity of unseen mass. Clusters grow by swallowing smaller groups, and voids expand as matter drains away into the denser regions. The cosmic web is dynamic, ever-evolving, shaped by the invisible tension between gravity and expansion. And within the web lie countless mysteries. Some galaxies sit at crossroads of filaments, growing rapidly and bursting with star formation. Others drift through voids, isolated and ancient, untouched by the commotion of crowded clusters. There are hints that the environment of a galaxy, the location it occupies in the web, can influence everything from its shape and color to the presence of life on its planets. There's even speculation that the universe's large-scale structure might resemble neural networks, leading to poetic parallels between the cosmos and the human brain. Though purely metaphorical, such analogies highlight a deep yearning to connect with the universe, not just in scale but in structure, in purpose, in thought. The cosmic web is not just a map of the visible, it is also a skeleton of the invisible. Dark matter forms its bones. Galaxies are merely the luminous traceries, like frost collecting on spider silk. To perceive this web is to touch the echoes of the universe's birth, to feel the pull of ancient gravity still shaping the stars. And yet, for all its grandeur, the cosmic web also reminds us of something humbling. The vast voids, the spaces between, are larger than anything we can easily imagine. They are cold, dark, and nearly empty. Galaxies are few and far between. Light from one end may never reach another. It is in this emptiness that we realize just how precious our little island of stars truly is. As we look outward and map the stars, we are also drawing inward toward deeper questions. What is the role of life in this web? Are we solitary observers, or is intelligence written into the structure itself? Are we flukes or fragments of a deeper pattern? In the next part, we will step beyond the edge of observable reality to the horizon of light itself and ask one of the most daring questions of all. Is our universe the only one? Or is it but one bubble in an infinite sea, the multiverse? To peer beyond the universe we know is to venture into speculation, but not aimless guessing, rather, into a frontier of bold theories built upon the scaffolding of rigorous mathematics and the echoing clues left in the cosmos itself. The idea of a multiverse, that our universe may be just one of many, is no longer confined to science fiction. It is a serious, though controversial concept being explored at the frontiers of cosmology, quantum mechanics, and string theory. Our observable universe is bounded not by walls but by light's limits. Because the universe is only 13.8 billion years old, we can only see as far as light has had time to travel. But due to the expansion of space, that observable bubble spans about 93 billion light-years in diameter. Beyond this edge, more space exists, perhaps infinitely more. And if it exists, might it hold more universes? There are several theories that attempt to describe how multiple universes, together called the multiverse, could exist. One such model emerges from cosmic inflation, the brief but exponential expansion that occurred fractions of a second after the Big Bang. According to this theory, space expanded faster than the speed of light, smoothing out irregularities and planting the seeds for galaxies. But inflation may not have ended uniformly. In some models, it's eternal. Pocket universes like ours continuously bud off from a vast, inflating cosmic foam, each with its own Big Bang, its own laws of physics, and its own destiny. This is the eternal inflation multiverse. Each of these bubble universes could be completely inaccessible to the others, separated by inflating space that prevents any signal or particle from ever crossing over. From this perspective, our entire observable universe might be a single bubble in an endless cosmic champagne, one sparkling speck in a sea of unknown others. Then there's the quantum multiverse, grounded in the strange rules of quantum mechanics. In the famous many worlds interpretation, every quantum event branches reality. Each decision, each particle interaction, leads to a splitting of the universe, creating a vast and rapidly multiplying tree of diverging realities. In this vision, there are universes where every possibility plays out, one where you turned left instead of right, one where the earth never formed, one where life never evolved. More radical still is the mathematical universe hypothesis, proposed by physicist Max Tegmark. It suggests that all mathematical structures exist physically in their own right. In this model, our universe is just one of countless structures described by consistent mathematical equations, each as real as ours, though potentially governed by entirely different logic or constants. And then there's string theory, a complex and ambitious attempt to unify all fundamental forces and particles into a single framework. In many versions of string theory, the number of possible solutions is staggering, on the order of 10,500 or more. Each of these solutions corresponds to a different universe with unique properties, constants, and dimensions. This vast landscape of possibilities has become known as the string landscape, and if realized, it implies a vast multiverse beyond imagining. Skeptics rightly question, if these universes are forever beyond our reach, can we ever verify their existence? Is the multiverse a scientific model or a philosophical musing? These are fair challenges, but indirect evidence such as the fine-tuning of physical constants or anomalies in the cosmic microwave background has sparked serious consideration. Why, after all, does our universe have the precise conditions necessary for life? Some argue that, in a multiverse, it's not surprising. We live in the universe where life is possible, simply because observers can only exist in such universes. Others seek observable signatures. Some hypothesize that if another universe ever collided with ours in the distant past, it might leave circular imprints in the cosmic microwave background, a faint scar from an interuniversal brush. So far, such evidence remains tantalizing, but unconfirmed. The multiverse forces us to redefine our sense of significance. If countless universes exist, does that make our own less special or more precious? Perhaps both. The multiverse can be humbling, but it also opens the imagination to the grandest scale of possibility. Not only is the universe vast, reaching across billions of light years, but the very notion of universe might itself be but a local dialect in a much larger cosmic language. And yet we return, inevitably, to the only stage we can observe, the only realm we can touch. The stars above us, the galaxies wheeling through the night, the atoms that compose our breath, all belong to this universe. Even if others exist, They are silent to us for now. Still, the multiverse remains a deeply compelling idea, not because it proves anything, but because it stretches the limits of our questions. It demands that we consider not only what we see, but also what could be. It shifts our view from a universe to a cosmic ecology, where possibility is the true landscape, and we, for all our smallness, are real. From the edges of our cosmic horizon, we now turn inward once again, not toward what lies beyond space, but toward what binds space itself. In the next part, we will explore the silent architect of structure, the unseen force shaping the fate of galaxies and the expansion of space. Dark energy, the great unknown accelerating our universe's growth. Into the infinite. The cosmos is an ocean expanding outward, carrying within it countless stars, galaxies, and the very fabric of space-time itself. Yet hidden beneath this grandeur lies a profound mystery, an invisible force pushing the universe apart, accelerating its expansion at an ever faster pace. This force, known as dark energy, governs the ultimate fate of the universe and challenges our deepest understanding of physics. To grasp the true scale of the universe, we must understand the role dark energy plays in shaping its vastness. Dark energy was first inferred in the late 1990s when astronomers studying distant supernovae discovered that, contrary to expectations, the universe's expansion was not slowing down due to gravity, but speeding up. This unexpected discovery earned the 2011 Nobel Prize in Physics and revolutionized cosmology. But what exactly is dark energy? It remains one of the greatest unsolved problems in science. Unlike matter or radiation, which pull things together through gravity, dark energy appears to have a repulsive effect, pushing galaxies away from each other with increasing vigor. It permeates all of space, a constant energy density that does not dilute as the universe expands. This property suggests that dark energy is linked to the vacuum of space itself, often described as the cosmological constant, a concept introduced by Einstein long ago but later discarded, only to be resurrected with new significance. If dark energy continues to dominate the cosmos, its repulsive influence will become more pronounced over time, stretching space faster and faster. Galaxies beyond our local group will eventually recede beyond our horizon, disappearing from view as space expands faster than light can travel. This cosmic acceleration redefines the limits of the observable universe, shrinking our window on the cosmos as more of it slips away. This accelerating expansion raises profound questions about the ultimate size of the universe. Is space infinite, or is it finite but unbounded like the surface of a sphere? If dark energy's density remains constant, space may continue to expand, forever leading to a cold, dark, and lonely cosmos, a scenario known as the Big Freeze. Over trillions of years, stars will burn out, galaxies will drift apart, and the universe will approach a state of maximum entropy, where no meaningful energy gradients remain to power processes or life. Yet there are other possibilities. Some models suggest dark energy might vary over time, fading away or reversing. If dark energy weakens, gravitational attraction could slow expansion or even reverse it, leading to a big crunch, a cosmic collapse back into a dense, hot state. Alternatively, if dark energy grows stronger, it might rip apart galaxies, stars, planets, and eventually atoms themselves in a scenario called the Big Rip. The precise nature of dark energy holds the key not only to the universe's future size, but to its origin and fundamental laws. Is dark energy truly constant, or is it an exotic field, dynamic and evolving? Experiments such as large-scale galaxy surveys and cosmic microwave background measurements seek subtle clues to its behavior. To measure the universe's expansion rate, astronomers rely on the Hubble constant, a value that describes how fast galaxies recede per unit distance. Yet, recent observations have revealed tension between measurements based on nearby objects and those inferred from the early universe's radiation, hinting at new physics beyond our current models. This Hubble tension might be a doorway to understanding dark energy's true nature. While dark energy shapes the vast, large-scale structure of the universe, it is intertwined with another cosmic mystery: dark matter, an invisible form of matter that binds galaxies together and sculpts cosmic webs. Together, dark matter and dark energy constitute about 95% of the universe's total energy content, with ordinary matter, the atoms we know, making up only about 5%. This cosmic composition further underscores the staggering scale of the universe. The light we see from stars and galaxies is but a faint glimmer within a vast, dark ocean of unseen substance and energy. To comprehend the true size and structure of the universe, we must grapple with these invisible components that govern its evolution. Looking outward, astronomers map the large-scale cosmic web, vast filaments of galaxies separated by enormous voids, regions almost empty of matter. This structure forms patterns on scales of hundreds of millions of light-years, reflecting the interplay of gravity, dark matter, and dark energy over billions of years. It is a universe not uniform but richly textured, a cosmic tapestry woven from the fundamental forces. As we deepen our understanding, we realize that the universe's true size is not just a number of light-years or megaparsecs. It is a dynamic, evolving entity, shaped by forces both known and mysterious, stretching the limits of space and time. Our observable universe may be a mere bubble in a vast cosmic ocean, its boundaries set by the finite speed of light and the accelerating expansion of space. Yet, even as we measure distances, map galaxies, and probe the invisible components, a profound truth remains. The universe is far vaster and stranger than our minds can fully grasp. It invites us to wonder, to explore, and to embrace the unknown. In the next part, we will journey into the realm of the very small, the quantum universe, and see how the tiniest scales of reality challenge and complement our understanding of cosmic size, revealing a universe both immense and deeply interconnected. As we step beyond the vast scales of galaxies and cosmic expansion, our journey into understanding the universe's size leads us inward, toward the fundamental fabric of reality itself, the quantum realm. Here, the rules of classical physics dissolve, replaced by the strange and fascinating laws of quantum mechanics. Though quantum scales are minuscule compared to cosmic distances, their role is crucial in shaping the universe's origin, structure, and ultimate fate. To truly comprehend how big the universe is, we must explore the intimate dance between the very large and the very small. Quantum mechanics emerged in the early 20th century as scientists grappled with the nature of light and matter. Experiments revealed that particles like electrons and photons exhibit both wave-like and particle-like properties, existing in a probabilistic haze rather than fixed trajectories. At these scales, uncertainty and indeterminacy govern, challenging our everyday intuitions. This quantum domain is not separate from the cosmos, but underpins it. The vacuum of space itself is alive with quantum fluctuations, tiny, ephemeral bursts of energy that spontaneously appear and vanish. These fluctuations have profound consequences. In the earliest moments after the Big Bang, quantum effects drove the rapid inflationary expansion of space, stretching tiny quantum fluctuations into vast cosmic structures that seeded galaxies and clusters. Moreover, quantum mechanics sets fundamental limits on measurement and knowledge. The famous Heisenberg uncertainty principle states that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time. This principle hints at a universe where the fabric of space and time is fuzzy, and the classical notion of a smooth, continuous cosmos may break down at the smallest scales. One of the greatest puzzles in physics today is reconciling quantum mechanics with Einstein's theory of general relativity, which describes gravity and the curvature of space-time on cosmic scales. These two pillars of modern science rest on fundamentally different mathematical frameworks, and unifying them remains a central quest. The reconciliation would provide insights into the nature of space, time, and the universe's size on both the largest and smallest scales. Some theoretical approaches, such as string theory and loop quantum gravity, propose that space-time itself has a discrete structure at the Planck scale, around 10⁻⁵ meters, far smaller than anything we can currently probe. If spacetime is quantized, then the continuous picture of an infinitely divisible universe might be replaced by a granular one, altering our understanding of cosmic scale fundamentally. Quantum entanglement, another remarkable phenomenon, links particles across vast distances instantaneously, suggesting a deep interconnectedness woven into the universe's fabric. Some physicists even speculate that spacetime geometry itself might emerge from patterns of quantum entanglement, offering a new paradigm where size and distance are emergent properties rather than fundamental givens. While the quantum realm seems disconnected from everyday experience, its principles influence the universe's size indirectly, yet decisively. The balance between quantum forces and gravity shaped the formation of stars, galaxies, and cosmic structure. Quantum vacuum energy relates closely to dark energy, the mysterious driver of cosmic acceleration we explored earlier. Furthermore, the interplay between quantum mechanics and cosmology touches upon the ultimate boundaries of the universe, whether it is finite or infinite, whether it loops back on itself or extends endlessly. Quantum cosmology models attempt to describe the universe's birth as a quantum event, a fluctuation from nothing that ignited the Big Bang and set the stage for cosmic expansion. In considering the size of the universe, we must embrace this intricate connection. The macrocosm and microcosm are intertwined, each informing and shaping the other. The vastness of galaxies and voids arises from quantum seeds, while the deepest nature of space and time remains a quantum mystery. This holistic view enriches our appreciation of cosmic scale. The universe is neither simply a collection of distant stars, nor an empty void, but a dynamic, quantum-infused cosmos, boundless yet finely structured, immense yet intimately connected. In the coming part, we will explore the nature of multiverses and parallel universes, contemplating whether our observable cosmos is just one of many, and what this means for the true extent of reality's size. As we venture further into the mysteries surrounding the universe's size, we encounter a concept that challenges even the boldest imaginations: the multiverse. The idea that our universe is but one among a vast or even infinite ensemble of universes radically redefines what we mean by the universe itself. If multiverses exist, the scale of reality transcends our familiar cosmic horizon, extending into realms unimaginably vast and diverse. The multiverse concept arises naturally from several areas of modern physics, including cosmology, quantum mechanics, and string theory. One pathway to multiverses emerges from the inflationary model of the early universe, which we previously touched upon. Inflation posits a brief period of exponential expansion, smoothing and stretching space. Some versions of inflationary theory propose that this expansion is eternal, spawning bubble universes that continually bud off from the inflating spacetime. Each bubble could harbor different physical constants, laws, and initial conditions. In this scenario, our observable universe is just one bubble among countless others, each potentially with its own unique properties. Some bubbles might be similar to ours, while others could be radically different, featuring alternate dimensions, varied particle types, or even entirely different fundamental forces. Parallel to inflationary theory, interpretations of quantum mechanics also suggest multiverse-like structures. The many worlds interpretation, for example, asserts that every quantum event branches reality into multiple parallel outcomes, each realized in its own world. This perspective envisions an ever-branching tree of universes, representing all possible histories and futures, intertwined yet distinct. String theory, a candidate for a unified theory of everything, introduces another multiverse angle. The theory's mathematical framework allows for an enormous number of possible vacuum states, potentially as many as 10 out of 500, each corresponding to a different universe with its own laws of physics. This string landscape underlines the possibility of a vast multiverse born from fundamental physics. If these multiverse ideas hold true, then asking, how big is the universe, becomes almost meaningless, as our universe is merely a tiny patch within an unfathomably vast meta-reality. The multiverse would be the ultimate container of all physical existence, stretching far beyond what any telescope or experiment could access. The implications of multiverses reach beyond physics and into philosophy and cosmology. They offer potential explanations for the fine-tuning of our universe's constants, why conditions appear so precisely set to allow life and complexity. If countless universes exist with varied parameters, it is not surprising that at least one like ours supports observers who can ask these questions. However, the multiverse remains highly speculative. Detecting or confirming other universes is extraordinarily challenging, as by definition, they lie beyond our observable horizon. Scientists seek indirect clues, such as cosmic microwave background, patterns hinting at collisions with other bubble universes, but evidence is tentative at best. Nevertheless, the multiverse concept expands our understanding of size on a cosmic scale. It invites us to imagine a reality that dwarfs even the grandest galaxies and clusters, a cosmic tapestry of infinite breadth and infinite variety. As we conclude this exploration, we return to a more grounded yet equally profound inquiry: the shape and topology of our own universe. Is it infinite, extending endlessly in every direction, or is it finite but unbounded, curving back on itself, like the surface of a sphere? The geometry of the universe shapes not only its size, but the very nature of space and time. Einstein's general relativity allows for several possible large-scale geometries: flat, positively curved, spherical, or negatively curved, hyperbolic. Measurements of the cosmic microwave background and large-scale structure suggest our universe is remarkably flat with a tiny margin of error, implying it may be infinite. Yet, even a flat universe could be finite. If it has a complex topology, imagine a 3D torus where traveling far enough in one direction brings you back to your starting point. Determining the universe's global shape remains a key goal of cosmology. Future observations mapping subtle patterns in cosmic background radiation and galaxy distributions may reveal clues to whether space loops back on itself or stretches infinitely. Understanding whether the universe is finite or infinite influences fundamental questions about size, scale, and existence. An infinite universe contains infinite matter, infinite galaxies, and infinite possibilities. A finite universe has boundaries, though perhaps boundaries without edges, imposing limits on the cosmic expanse. As our journey through cosmic scale progresses, we confront the tension between the measurable and the unimaginable. The universe is a grand paradox. It is both known and unknown, vast yet accessible through the human mind and technology. In the next part, we will dive into the role of dark matter and dark energy, the invisible majority that governs the universe's mass energy content and shapes its expansion and structure. As we move forward, our understanding of the universe's vastness must incorporate its unseen components, dark matter and dark energy, because they profoundly influence both the structure and fate of the cosmos. Although invisible to telescopes, these mysterious entities together constitute approximately 95% of the universe's total mass energy content, with ordinary matter, the stuff of stars, planets, and people, making up only about 5%. To grasp how big the universe truly is, we must first appreciate the role these elusive components play. Dark matter was first inferred through observations of galaxies and galaxy clusters. When astronomers measured the rotational speeds of galaxies, they found stars moving too rapidly to be held together solely by visible matter's gravity. There must be an unseen halo of matter exerting gravitational pull. This invisible mass, now called dark matter, permeates galaxies and clusters, acting as cosmic scaffolding that shapes large-scale structure. Without it, galaxies as we know them would not have formed. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it effectively invisible. It interacts primarily through gravity, revealing itself only by its gravitational influence on visible matter and light bending, called gravitational lensing. though its precise nature remains unknown. Candidates include exotic particles such as WIMPs, weakly interacting massive particles, or axions. Dark energy, discovered more recently in the late 1990s, is even more mysterious. It is the name given to the unknown force causing the accelerated expansion of the universe. By studying distant supernovae, astronomers found that the universe's expansion is not slowing due to gravity as once expected, but actually speeding up. This acceleration implies the presence of a pervasive energy that pushes space apart. Dark energy behaves like a negative pressure spread uniformly throughout space, counteracting gravitational attraction on the largest scales. Its effect dominates the cosmic budget today and dictates the ultimate destiny of the universe, whether it will expand forever, slow down, or even contract. Together, dark matter and dark energy shape the universe's size, structure, and evolution. Dark matter's gravitational pull binds galaxies and clusters, while dark energy drives cosmic acceleration, stretching the fabric of space itself. This interplay determines how large and how fast the universe grows. Understanding their influence allows us to comprehend why the observable universe extends as far as it does, and why it will continue to expand beyond the reach of our instruments. The accelerating expansion means distant galaxies recede faster and faster, eventually disappearing beyond the cosmic horizon, unreachable forever. This dynamic universe with hidden components complicates our picture of size. The observable universe is limited by the speed of light and cosmic expansion, but beyond lies the unobservable universe, potentially infinite, shaped by dark energy's mysterious force. Our cosmic horizon marks the boundary of what we can see and measure, but space itself may continue infinitely. The study of dark matter and dark energy also opens profound questions about the fundamental laws of physics and the ultimate nature of reality. Are these entities signs of new physics beyond the standard model? Do they hint at unknown fields, particles, or dimensions? Scientists worldwide seek answers through particle accelerators, underground detectors, space telescopes, and sophisticated simulations. As the universe expands and evolves under these invisible influences, its size and fate remain among the greatest questions of modern science. Will acceleration continue forever, driving galaxies beyond our sight and isolating cosmic islands in an ever-growing void? Or will new physics change the story, altering the universe's expansion and structure? The exploration of dark matter and dark energy reveals that the universe's vastness is not merely a matter of distance or scale, but also of complex hidden forces shaping cosmic destiny. These forces challenge us to expand our understanding, pushing beyond what is visible and measurable. In the next part, we will delve deeper into the cosmic microwave background, the afterglow of the Big Bang, and how this faint radiation maps the early universe and informs us about its size and shape. The cosmic microwave background, CMB radiation, offers a unique window into the early universe, revealing its origins and providing a cosmic map that helps us understand the universe's size and structure. This faint glow of microwave radiation fills all space and is the remnant heat left over from the Big Bang, dating back nearly 13.8 billion years. When the universe was only about 380,000 years old, it was a hot, dense plasma of photons, electrons, and protons. At this time, photons were constantly scattered by free electrons, making the universe opaque. As the cosmos expanded and cooled, it reached a temperature where electrons combined with protons to form neutral hydrogen atoms, allowing photons to travel freely. This moment is known as recombination, and the released photons form the CMB we observe today. The CMB is remarkably uniform, but contains tiny fluctuations, minute variations in temperature on the order of 1 part in 100,000. These fluctuations represent the seeds of all cosmic structure, galaxies, stars, and clusters that formed over billions of years from the gravitational growth of these initial irregularities. By studying the detailed pattern of these temperature fluctuations, scientists can infer the geometry, size and composition of the universe. Observations from satellites like COBE, WMAP, and Planck have mapped the CMB with extraordinary precision, confirming that the universe is flat on large scales, meaning its geometry follows Euclidean rules. This flatness has profound implications for size. In a flat universe, the total spatial extent can be infinite or very large, with no intrinsic curvature to cause space to loop back on itself. Measurements indicate that the observable universe forms a spherical volume around us with a radius of about 46 billion light-years, much larger than the simple product of the universe's age and the speed of light due to cosmic expansion. These results also support the inflationary theory, which proposes that the universe underwent an extremely rapid exponential expansion fractionally after the Big Bang. Inflation stretched any initial curvature, smoothing out space to appear flat and homogeneous on large scales. This rapid growth also explains the uniformity and specific patterns observed in the CMB. Despite the detailed map of the observable universe, the CMB leaves unanswered questions about the global size of the entire universe beyond what we can see. The universe might extend infinitely or be so large that its curvature is undetectable within our observational horizon. The CMB's discovery and study represent one of the greatest achievements of cosmology, providing a direct glimpse into the universe's infancy and a fundamental tool for measuring its size and composition. Understanding the CMB also sheds light on the universe's expansion history, connecting the earliest moments to its current accelerated expansion driven by dark energy. The radiation's uniform temperature and tiny anisotropies link the smallest quantum fluctuations of the primordial universe to the immense cosmic web observed today. As we trace this cosmic journey, the size of the universe transforms from a simple distance to a complex concept intertwined with the physics of space, time, and matter. Each new observation refines our knowledge, expanding the boundaries of what we call the universe. In the upcoming part, we will explore how galaxies cluster and form large-scale structures, and how these cosmic webs reveal the universe's immense scale. The large-scale structure of the universe is a magnificent cosmic web of galaxies, clusters, filaments, and voids that stretches across hundreds of millions of light-years. This grand architecture reveals the universe's immense scale and the dynamic processes shaping its evolution. Galaxies are not scattered randomly, but are arranged in clusters, gravitationally bound collections of hundreds or thousands of galaxies. These clusters themselves connect through vast filaments of matter, forming a network that looks like the strands of a spider's web. Between these filaments lie enormous voids, vast regions of near-empty space spanning tens of millions of light-years. This cosmic web structure is a direct consequence of gravity acting on the initial fluctuations visible in the cosmic microwave background. Tiny irregularities in matter density grew over billions of years, pulling matter into denser regions and creating the filamentary patterns we observe. Mapping this large-scale structure helps astronomers estimate the size and shape of the universe. By surveying millions of galaxies, projects like the Sloan Digital Sky Survey have revealed the vastness and complexity of this cosmic scaffolding, which extends far beyond the limits of our local galaxy group. The observable universe is a sphere with a radius of about 46 billion light-years, but the distribution of galaxies within it spans distances so vast that light itself takes billions of years to travel between them. Even the nearest galaxy clusters, like the Virgo cluster, lie tens of millions of light-years away. Understanding these distances involves accounting for the universe's expansion. Space itself stretches, increasing the distance between galaxies over time. When we observe distant galaxies, their light is redshifted, shifted toward longer wavelengths, indicating that they are moving away from us. The farther a galaxy, the greater its redshift, and the faster it appears to recede. This redshift distance relationship, first discovered by Edwin Hubble, is the foundation for modern cosmology and provides a direct measurement of the universe's expansion rate, known as the Hubble constant. However, measuring the Hubble constant has proven challenging, with different methods yielding slightly different values. This tension in measurements hints at deeper mysteries within cosmology and may point to new physics beyond our current understanding. Beyond galaxy clusters and filaments, the universe contains dark matter and dark energy, mysterious components that dominate its total mass energy content but remain invisible and enigmatic. Dark matter, inferred from gravitational effects on visible matter and light, forms the unseen backbone of the cosmic web, anchoring galaxies and clusters. Dark energy, on the other hand, drives the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing pace. Together, these components shape the universe's large-scale structure and influence its ultimate fate. Whether the universe will expand forever, slow down, or collapse depends on the interplay of dark energy, dark matter, and ordinary matter. The vastness of the universe becomes even more apparent when considering cosmic time. Observing distant galaxies is like looking back in time, as their light has traveled billions of years to reach us. We see them as they were in the distant past, witnessing different epochs of cosmic history. This temporal dimension adds a layer of complexity to the universe's size. The observable universe is a sphere not only in space but also in time, with the cosmic horizon marking the limit of what we can see due to the finite speed of light and the universe's finite age. Ultimately, the universe's true size may be infinite, or it may be so large that its boundaries lie forever beyond our observational reach. As we continue to explore, the universe reveals itself as an intricate tapestry of space, time, matter, and energy, a grand cosmic symphony whose scale is both humbling and inspiring. In the next part, we will delve into how the fundamental forces of nature govern the universe's behavior on the largest scales and shape its destiny. The vastness of the universe is not merely a matter of distances, but also of the fundamental forces that govern its behavior and structure. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These four pillars of physics dictate how matter interacts and how the cosmos evolves over time. Among them, gravity plays the most crucial role in shaping the large-scale structure of the universe, pulling matter together to form galaxies, clusters, and the cosmic web. Without gravity's relentless pull, matter would remain a nearly uniform soup, never condensing into the stars, planets, and galaxies that populate the heavens. Gravity operates on every scale, from the smallest particles to the grandest cosmic structures. It is the architect of cosmic evolution, responsible for the collapse of gas clouds that birth stars, for the orbits of planets, and for the majestic spiral arms of galaxies. Yet gravity is also intimately linked with the fabric of space and time itself, as described by Albert Einstein's theory of general relativity. This theory revolutionized our understanding of gravity, showing it not as a force acting at a distance but as the curvature of spacetime caused by mass and energy. In this geometric view, massive objects like stars and black holes warp the spacetime around them, guiding the paths of other objects and light rays. This curvature is not confined to local scales but extends throughout the cosmos, influencing how galaxies move and how light travels across billions of light years. The bending of light by gravity, known as gravitational lensing, allows astronomers to probe the distribution of mass, including invisible dark matter, across the universe. Dark matter remains one of the greatest mysteries in cosmology. While it cannot be seen directly, its gravitational effects are unmistakable. Galaxies rotate faster than expected based on visible matter alone. Clusters show gravitational fields that defy the mass we observe, and light from distant objects bends in ways that reveal unseen mass. This invisible substance makes up about 27% of the universe's total mass energy budget, vastly outweighing ordinary matter. Complementing dark matter is dark energy, an even more perplexing component that constitutes roughly 68% of the universe's total energy. Discovered in the late 1990s through observations of distant supernovae, dark energy is driving the accelerated expansion of the universe. Instead of slowing down due to gravity's pull, The cosmos is stretching faster and faster, pushing galaxies away from each other with increasing speed. The nature of dark energy remains unknown. It might be a property of space itself, a cosmological constant first introduced by Einstein and later abandoned, or a dynamic field that changes over time. Understanding dark energy is one of the most pressing challenges in modern physics and cosmology. Together, dark matter and dark energy shape the fate of the universe. Will the cosmos continue expanding forever, growing colder and emptier until stars burn out and galaxies fade? Or will some unknown force reverse this expansion, leading to a cosmic collapse? Current evidence favors eternal expansion, but the final destiny is still a subject of active research and profound mystery. On smaller scales, the other fundamental forces, electromagnetism and the nuclear forces, govern the behavior of atoms and molecules, enabling the chemistry that leads to life. The delicate interplay between these forces underpins the complexity and diversity of the universe, from the formation of water molecules to the emergence of biological organisms. The vastness of the universe is thus matched by the depth of its physical laws. Exploring these laws helps us comprehend not only how big the universe is, but also why it is the way it is. Every star we see, every galaxy mapped, and every cosmic background photon detected carries within it clues to the grand cosmic story. As we journey onward, we will explore how human curiosity and technology have expanded our horizons, allowing us to measure cosmic distances, observe the faint glow of the early universe, and push the boundaries of what is knowable. As we delve deeper into the question of the universe's vastness, it becomes essential to consider how humanity has come to measure and comprehend these immense distances. The history of cosmic measurement is a testament to human ingenuity, perseverance, and the evolution of scientific thought. From the earliest observations of wandering stars to the latest observations by space telescopes, each step has expanded our view of the cosmos exponentially. The first significant milestone in measuring cosmic distances was the determination of the distance from Earth to the Sun, known as the astronomical unit, AU. Ancient Greek astronomers like Aristarchus and Hipparchus made early attempts at this measurement through clever geometric methods. Later, during the Renaissance, astronomers refined these calculations using transits of Venus and parallax measurements. Parallax is the apparent shift in position of a nearby object relative to distant background objects when viewed from different vantage points. This method is fundamental in astronomy for gauging distances to stars within our galaxy. By observing a star's position at different times of the year as Earth orbits the Sun, astronomers calculate its distance with trigonometric precision. However, parallax works effectively only for stars relatively close to us, within a few thousand light-years. Beyond this range, stars appear too faint, and the parallax angles too minuscule to measure accurately. To reach farther into space, astronomers developed the concept of standard candles, objects whose intrinsic brightness is known, allowing their distances to be inferred from how bright they appear. Cepheid variable stars are classic examples of standard candles. Their pulsation periods correlate with their true luminosities, providing a cosmic yardstick to measure distances across millions of light-years. By observing Cepheids in nearby galaxies, astronomers began to map the structure of the Milky Way's neighbors and beyond. The discovery of Type Ia supernovae as reliable standard candles revolutionized distance measurements even further. These spectacular stellar explosions have a consistent peak brightness, enabling the measurement of distances to galaxies billions of light-years away. Observations of distant supernovae led to the discovery of the universe's accelerating expansion, providing critical evidence for dark energy. In parallel, astronomers have relied on redshift, the stretching of light toward longer wavelengths, as a tool to estimate how far away galaxies are. The universe's expansion causes the light from distant galaxies to be shifted to the red end of the spectrum, with the amount of redshift correlating with distance. Measuring redshift through spectroscopy allows the construction of large-scale maps of the universe, revealing its vast cosmic web. Modern observatories like the Hubble Space Telescope and the upcoming James Webb Space Telescope have pushed the boundaries of observation further, peering back in time to the earliest galaxies formed shortly after the Big Bang. By detecting faint infrared light from these ancient objects, astronomers explore the universe's infancy and the emergence of structure. The cosmic microwave background radiation, the afterglow of the Big Bang, provides yet another measure of the universe's size and age. Detected as a nearly uniform glow of microwaves permeating all of space, it encodes information about the universe's composition, expansion history, and geometry. Satellites such as COBE, WMAP, and Planck have mapped this relic radiation in exquisite detail, helping to refine the cosmological parameters that describe our universe. The measurements collectively suggest that the observable universe extends approximately 46.5 billion light-years in every direction, encompassing all the matter and energy that we can detect or infer. But this observable horizon is only a fraction of the entire cosmos. The total universe might be infinitely large or so vast that it dwarfs even the observable portion by unimaginable scales. Such enormity challenges our perception and comprehension, raising philosophical and scientific questions about the nature of reality, the possibility of other universes, and the ultimate limits of human knowledge. Yet, it is precisely this mystery and scale that inspire ongoing exploration and discovery. From the humble beginnings of stargazing to the grandest telescopes and probes, our quest to understand how big is the universe really continues to unfold, revealing layers of complexity and wonder that enrich our place in the cosmos. As we continue exploring the vastness of the universe, it is important to understand the difference between the observable universe and the universe as a whole. The observable universe refers to the portion of the cosmos from which light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. This creates a spherical boundary around Earth, extending about 46.5 billion light-years in every direction, owing to the universe's expansion. However, the universe beyond this observable sphere remains hidden from us because light from those regions has not had enough time to arrive. The total universe might extend infinitely, or it could be finite but unbounded, much like the surface of a sphere. Such possibilities are described by cosmological models depending on the universe's curvature and topology. The geometry of the universe plays a crucial role in these models. Current evidence strongly supports a flat universe with zero or near zero curvature on large scales, as indicated by measurements of the cosmic microwave background radiation and galaxy distributions. In a flat universe, space extends infinitely in all directions, but this does not necessarily mean that the amount of matter and energy is infinite, only that there is no global curvature to curve space back on itself. One intriguing question that arises is whether our universe is just one part of a much larger multiverse, a concept arising from some interpretations of quantum mechanics and inflationary cosmology. In such scenarios, countless other universes might exist with different physical laws and constants, each a bubble in an enormous cosmic foam. While such ideas remain speculative, they highlight how our understanding of the universe's size touches on profound questions about existence itself. How do we define the universe's boundaries, if any exist? Is it even meaningful to speak of a size in an infinite cosmos? Returning to the observable universe, its vastness can be illustrated by comparing scales. Our solar system is about 100 astronomical units across, a minuscule speck in the Milky Way, which spans about 100,000 light-years. Our galaxy is but one of hundreds of billions within the observable universe, arranged in clusters and superclusters forming a vast cosmic web. Distances to faraway galaxies are often expressed in billions of light-years, meaning the light we see from them started its journey long before humanity existed. When we gaze at a galaxy 10 billion light-years away, we see it as it was 10 billion years ago, offering a glimpse into the universe's past and evolution. The sheer scale forces us to reconsider our place in the cosmos. Humans are but a small part, of an immense dynamic universe filled with stars, galaxies, dark matter, and mysterious dark energy. Each discovery deepens our awe and curiosity, inviting us to explore further with new technologies and ideas. As we advance, future missions like the Extremely Large Telescope and space-based observatories promise to uncover even more distant and faint objects, pushing the limits of the observable universe. Simultaneously, theoretical work in physics and cosmology strives to understand the fundamental nature of space, time, and the universe's ultimate fate. In contemplating the enormity of the universe, we are reminded of the delicate balance between the known and the unknown, the measurable and the mysterious. The universe's true size remains one of science's greatest questions, an ever-expanding frontier that challenges our imagination and drives our quest for knowledge. As we delve deeper into the mysteries of the cosmos, we confront the challenge of understanding the ultimate fate of the universe, a question intimately connected to its size, expansion, and composition. The universe is not static. It has been expanding since the Big Bang, a discovery first observed by Edwin Hubble in the 1920s through the redshift of distant galaxies. This expansion continues today, but with surprising acceleration. Dark energy, a mysterious form of energy that permeates space, is thought to drive this accelerating expansion. Accounting for approximately 68% of the total energy density of the universe, dark energy's repulsive effect causes galaxies to move away from each other faster over time. The consequences for the universe's size are profound. Regions currently within our observable universe may eventually move beyond our ability to see or communicate with them, effectively shrinking our cosmic horizon. Understanding dark energies. Nature is one of modern cosmology's grand challenges. Is it a cosmological constant, a fixed energy density inherent to space itself? Or is it a dynamic field changing over time? These questions link directly to the universe's geometry, age, and size evolution. Cosmologists use the Friedmann equations derived from Einstein's general relativity to model the universe's expansion based on its energy content: matter, radiation, dark matter, and dark energy. These models predict various possible futures, from a big freeze, where expansion continues forever, cooling and diluting matter, to a hypothetical big rip, where acceleration eventually tears apart galaxies, stars, and even atoms, or a big crunch, if gravity were strong enough to halt expansion and cause a collapse. Each scenario offers a different perspective on the universe's scale over time, either infinite growth or eventual contraction. While current data favors an ever-expanding cosmos, ongoing observations and theoretical developments may refine or reshape this view. Another intriguing dimension to consider is time itself. Woven inseparably with space into the fabric known as spacetime, the expansion of the universe stretches not just distances, but also influences how time passes relative to observers in different gravitational or velocity conditions. This intertwining of space, time, and gravity underpins our understanding of the cosmos and challenges intuitive notions of size and duration. Moreover, the question, how big is the universe, takes on new meaning when we consider quantum gravity theories, such as string theory and loop quantum gravity, aiming to unify general relativity and quantum mechanics. These frameworks suggest that space and time might have discrete structures at the Planck scale, vastly smaller than atoms, hinting at a fundamentally granular nature of reality. While such concepts remain theoretical and far from experimental confirmation, they reveal the layers of complexity in defining the universe's size and structure. The observable universe is but a stage for deep questions about the nature of existence, infinity, and the limits of human knowledge. Ultimately, exploring the universe's size is more than measuring distances. It is a journey into the heart of cosmology, physics, and philosophy. It is a testament to humanity's enduring curiosity, creativity, and desire to comprehend the cosmos we inhabit, a cosmos that continually expands, challenges, and inspires. As we reach the culmination of our journey through the vastness of the cosmos, we reflect on the profound insights and enduring mysteries that define the universe's true scale. The question, how big is the universe, transcends simple measurement. It invites us to embrace wonder, humility, and the relentless pursuit of knowledge. From the earliest stars to the most distant quasars, from the familiar spiral arms of our Milky Way to the cosmic microwave background radiation, the faint afterglow of the Big Bang, the universe reveals itself as a tapestry woven with light, matter, energy, and the very fabric of space-time. Despite humanity's incredible technological advances, our observable universe remains only a fraction of the whole. Beyond the cosmic horizon, countless galaxies, stars, and perhaps other forms of life await discovery, forever beyond our reach yet inspiring our imagination. Our exploration has also shown that the universe is not static or finite in a simple. It is dynamic and expanding, shaped by forces both visible and invisible, from gravity to dark matter and dark energy. It is a universe where space itself grows. Time flows differently depending on perspective, and the fundamental nature of reality may be more intricate than ever imagined. As science progresses, new instruments, missions, and theoretical breakthroughs will continue to push the boundaries of what we know. The James Webb Space Telescope and future observatories promise to peer deeper into cosmic history, revealing earlier epochs and shedding light on the universe's birth and evolution. Moreover, the quest to understand the universe's size is intertwined with questions about its origin and fate, about whether it is infinite or finite, closed or open, eternal or transient. These questions resonate with philosophical and existential dimensions touching on the place of humanity in the cosmos. In contemplating the universe's immensity, we are reminded of the fragile planet we call home and the delicate conditions that allow life to flourish here. The vastness of space highlights both our insignificance in the grand scale and the extraordinary privilege of conscious existence. Ultimately, the universe's size is a gateway to awe and inspiration. It challenges us to keep exploring, questioning, and dreaming. It invites us to appreciate the beauty of the stars, the complexity of nature's laws, and the infinite possibilities that lie beyond the known. So how big is the universe really? It is as big as our curiosity, as vast as the light traveling across eons, and as boundless as the human spirit seeking understanding. This journey never truly ends. It expands with each new discovery, each new question, and each new star we gaze upon. Thank you for joining this exploration into the depths of cosmic scale and wonder. If you enjoyed this journey, please like, share, and subscribe to continue exploring the universe with us.